We're going to do some deep learning for more advanced image recognition. We're going to do some facial recognition and some gesture recognition. Hi, and welcome to a video where we take a look at understanding convolutional neural network design and training. So now let's proceed to understanding the basic structure of a convolutional neural network. So as you've seen in the last chapter, convolutional layers then use the ReLU activation, which then use max pooling, then the dense or fully connected layer before we go to the last layer where we output the classes. Now, all CNNs basically follow this simple structure here. And however, the differences can be, we can have multiple convolutional layers. You can have multiple dense layers. You can have dropout in between. You can have max pooling in between different layers as well. And in the convolutional layers themselves, you can have different parameters we can mess with. Things like stride, things like the kernel size, how many convolutional filters you want. So these are just things to think about, but essentially they all basically follow the same structure we used in the last convolutional neural network in chapter 4.5 and 4.6. Well, we actually saw it in 4.6, so that's the one I'm referring to. So now these are some basic design rules you're going to want to know, and you're going to want to probably look back at this slide every so often in future when you're building your own convolutional neural network. So typically, the input size should be a square. So we've seen in MNIST it was 28 by 28, can be 64 by 64, can also be 222 or 229, I believe. That's CIFAR image sizes. Just so you know, this isn't necessary, but it simplifies our design. So you don't have to think about some things when you're actually using square images, and it speeds up our matrix calculations a lot as well. So also, here's another thing to think about. Input should be divisible by 4, which allows for downsampling. So you can see these are both divisible by 4, which helps with downsampling. It doesn't actually, it's not a rule, but it's just a good guideline to stick with. Also, typically, convolutional filters are 3 by 3 or 5 by 5. You can have bigger filters as well. VGG, I know, has a lot of different combination of filter sizes in its design. You can use different number of strides. Typically, you're going to want to use a stride of 1 when it's 2 or more if it's larger inputs, like the one for CIFAR, which is 229 by 229, I believe. Also, just so you know, you've seen what zero padding is. Zero padding is used to typically allow the output convolutional layer to be the same size as the input. That way you can chain multiple convolutional layers together. You can have like a sequence of maybe 4 or 5. And if you use zero padding in between, you don't actually reduce the size of the image. So you actually still retain a lot of information still. So that way you can actually build more complex layers in the network later on. Pooled kernel size is typically, as max pooling, is typically 2 by 2. It's a general good guideline to stick with. And also should note, dropout is a very easy to use and useful technique to avoid overfitting in CNN. So it's something I use quite often. It does increase the training time, unfortunately, but we're going to have to live with that. So now let's look at the other things we can think about for design rules. The more hidden layers you have, the more features, particularly high-level features, a CNN can learn. So I like to use a minimum of 2, which is what we have in the diagram right here. Diagram below, this one. However, typically you can use at least 3 if you have a complex image data set. So the reason for that is because low-level layers, that's the first layer here, learn simple details like edges, mid-layers learn simple structures, and higher layers, these are the last ones here, learn more complex structures. And this is a simple flow which we've seen before. We have conv pool. That's the one for this one right here. So that's generally some basic guidelines in designing CNNs. So now let's talk about loss functions. Now, loss functions are integral in training neural nets and convolutional neural nets, as they measure the inconsistency or difference between the predicted results and the actual targets, which you've seen before. They're always positive, and they penalize big errors as well. The lower the loss, the better the model, and many common loss functions are things like mean squared error and mean absolute error, that's MAE, and mean bias error, hinge loss. There's a bunch of different ones. MSE is a very easy one, a common one which we use. Now let's look at how we choose loss functions. So remember, we have things like categorical cross entropy and binary cross entropy. That's when you use it for different, basically 2-class problems, binary or categorical cross entropy. I'm not going to go into the details of what cross entropy and those things are. This is just general rules of thumb in this section. Also note the final activation layer when you use 2 or more classes is softmax. If it's just 2 classes, you use sigmoid. Now let's talk about optimizers, or how we choose optimizers. So now, generally, I will always use either stochastic gradient descent, SGD, with a decent learning rate of say 0.01 or maybe 0.001. Adam also in the adaptive rate optimizers. Adaptive rate means that they change their learning rate dependent upon the results it's being fed back in. So Adam is quite good. RMS prop is actually quite good too. They're all pretty good actually, to be fair. But I would like to start off using this and then maybe adjust things, or then start using this Adam as well. Now, what is loss and accuracy? Now, I mean, probably know this already, but loss and accuracy are important. And what loss is, remember we have loss functions which are trying to minimize the actual predicted results, the error in it, from what is actually the true labels. So loss you would expect. How does loss and test loss relate to each other? And accuracy as well. And this can help you understand overfitting as well. So as you train, the number of epochs you train, you expect your training loss, that's the one in red here, to go down naturally. It's always going to happen, okay? And accuracy is probably always going to go up for training accuracy as well. But what can happen with test accuracy and test loss? Look at the green one here. This is test accuracy. Test accuracy in this case never seems to get higher than, say, 45%. It's always hovering around this section here, despite the training loss and accuracy getting to better values, okay? Loss going down to 0 and accuracy going up here. And you can actually see the test loss actually here is going up slowly. So what's happening here is that your model is overfitting to the training data, and it's not basically working well on the test data at all. It's actually getting worse here because the loss is going up. So what's effectively happening in here is that you need to add maybe some more dropouts, some more complexity to your model. Even look at different things like data augmentation, because your model is overfitting. That is why these graphs that we plotted in the previous video section are so important to analyze. So now let's talk about epochs. So what exactly are epochs? So remember I mentioned this in the section where we're looking at the code? Well, an epoch occurs when a full set of our training data is passed or forward propagated and then back propagated through our neural network. After the first epoch, we will have a pretty good set of weights. However, by feeding our training data again and again into a neural network, we're continuously improving the weights and lowering our loss on the training data, at least, in our neural network. This is why we train for several epochs or iterations. So iterations are something different here. Usually at least 50, but I mean, at least 10 is usually quite good. 50 plus is ideal. What about batches? So what exactly are batches? So unless we had huge volumes of RAM, we simply can't pass all our training data into our neural network during training. We need to split this data into segments. So that segments are called batches. So batch size is the number of training samples we use in a single batch. So example, say we had 1,000 samples of data, 1,000 numbers in this case, or the last case you remembered. So let's say we specified a batch size of 100. In training, we take 100 of those samples of that data and use it to forward and back propagate it through our network to update our weights. If our batch size was indeed 1, which is a much smaller batch size, we're just simply exercising or doing stochastic gradient descent at that point, okay? Now, it is a bit debated whether batch size matters or whether it's important to have larger batch sizes or not. To be fair, in my experience, I do get better results when I use slightly larger batch sizes, which means that better hardware is going to give you better results, sometimes faster. However, it doesn't really impact it that much. So once you use a batch size that you can fit all the data into one pass, load your data, and then pass it through the network, it should be fine. Okay, so maybe a minimum of 16 would be good, dependent upon the image size, if your hardware can support it. Now, let's talk about iterations. So many people confuse iterations and epochs, including myself at one time. However, the difference is quite simple. Iterations are just a number of batches you need to complete one epoch. So again, in the same example, if we had 1,000 items in our data set and we set our batch size to 100, we need 10 iterations to complete one epoch. It's that simple. So what have we learned? We've learned some general rules and guidelines when designing CNNs. You've learned a bit about loss functions and optimizers. You've actually learned what overfitting is and how to analyze the graphs. And you've learned a bit about what batches, epochs, and iterations are. So now let's move on to the next section where we take a look at gesture recognition using the sign language MNIST. So stay tuned for the next video. Thank you.